Right. So the idea is that whether, or the question he was asking is that there is indication of subduction initiation in many regions associated with Tethys, especially in Turkey and in Oman. These are all places where he did field work. And question, which geodynamic processes trigger the formation of new subduction zones? The setting is that you have indications of so-called metamorphic sols in Oman and Turkey, both around 104 million years. So those sols are basically the material that has been subducted by plate convergence and then come up to the surface. And according to what they find is that a supra-subduction zone spreading only happened after those sols were created. So their conclusion was that it means that this was not spontaneous subduction, but it must have been forced by far-field forces. So first the subduction has been forced, and then as a consequence, the supra-subduction spreading has started. And then the question was, what is the cause for these far-field forces? And also, they found that the ophiolites formed at north-south trending supra-subductions. So ophiolites, these are the rocks associated with subduction, that they formed at north-south trending supra-subduction zone ridges and subduction segments. So the convergence would have been east-west, and because the subduction zones were trending in a north-south direction. This came from reconstructing those remains, which have, of course, strongly been deformed since then, using paleomagnetism. So, yeah, so this was the kinematic restoration shows that the Neo-Tethys subduction zone runs from a triple junction in the Eastern Mediterranean round to Western Indian Ocean. So it's all this region is subduction zones, and then it transitions into a rift ridge that opens the Mascarene Basin. So the plate motion was sort of spreading in the south and convergence in the north. And there was also this so-called Morondova plume, which caused the Morondova lip in Madagascar. And it was predating the subduction zone 10 to 15 million years. And so the question is whether this plume could be somehow related to this subduction initiation. And about the mechanism, I will come back in a moment, but first we have to go on talking a bit more about the features. So could this Morondova plume have caused the hemispheric plate boundary formation? In order to develop slabs long enough for self-sustained subduction, which is about 100 kilometers, requires only about 1 degree of India-Africa plate rotation. So could the plume induce this 1 degree rotation, and could this be caused by the Morondova plume push? Now, I think now we can probably go on to the Bildschirmpräsentation again. I'll try at least. So this is some work I did with Dawe in 2011. So we use the plume that pushes from below and pushes a plate, and we compute how much plate motion there can be induced. And we did this for one thing for the Deccan plume, and secondly for the Morondova plume. Firstly, just assuming the plume is at a hemispherical plate and pushes the plate to the side. And the second, these are the dashed lines or dotted line, and then the continuous line, if you take the actual plate geometry into account. And with this, we found that you can get about a few centimeters per year plate motion. And also what's important is that the plume push already starts about 15 million years before the plume reaches the surface. For example, the Morondova plume it reaches the surface around 90 million years, but while the plume head is rising, it already starts pushing. So it could start plate motions already around 105 million years ago. Now we have this dot here again. So I think we have to go out of this again. Right, so that is the main point, is that it's 105 million years ago, or that it's about 50 million years can predate. Now, we go on to the next part of the story. So that was when I had already come to a GFZ, and then around 2009, and then Stefan told me, well, he has this, there is this practicant from Jena who wants to do a practicum at our institute, and he thinks he's really good, and whether I can't think of some project for him to do. And then I thought of what I can do. Well, I thought that this model which I ran was without lateral viscosity variation. So maybe I can ask him to use the sitcom code. That was a time before aspect existed. So use sitcom, which has lateral viscosity variations, and compute the same thing. And then, yeah, okay, then I told him, well, why don't you use sitcom to do the same thing? And then he said, sure, I'll do that. And he did it all by himself. I had never used sitcom before myself, but he figured it all out. And so these were the results we got. So the basic result was that in the beginning, the plume head force is similar to the other case, but then the plume sort of feeds into this layer below the lithosphere with low viscosity material. So the draining of the source region, so that means because the plate motion gets decoupled, there's actually a lot less plume push that can be induced by this plume feeding into the low viscosity asthenosphere. And of course, this practicant, he came later to be a PhD student with me. That was René Gassmüller. And if any of you haven't met him, I'm sure you have been in contact with him, because he's now one of the main developers and maintainers of Aspect. And so it's very good still to have good contact with him in this way. Right. So that was in 2011. So we computed how much push the plume can give. But then Daue thought, well, there is, how can we get this plate rotation to be induced? And well, of course, the right way as a modeler to do this would be you set up a model with a plume and with a sort of maybe some plate boundary, and you see whether that can give you something like subduction initiation. But then, of course, then I thought that's probably, if I do that, probably run 100 models and I still don't get what I want. So I was not very confident that I could get anywhere with modeling. And also, I didn't have any talented practicant or anybody else to work with me. So I thought if I do something a lot simpler, so just some simple analytical or conceptual model to see whether that's really this plume could contribute something sufficient, right? And in order to show that, I developed some kitchen table counter experiment, which I'm going to show you now, and you got to tell me whether you have the sound also. If you don't have the sound for this, then I will narrate it myself.
I don't hear anything.
Huh? Can you hear it?
No.
No sound.
No sound. Okay, then I'll narrate this myself. So these are, yeah, then I have to turn the sound off myself also, otherwise it irritates me. Okay, so this shows basically the two plates, and this dot here, this is where the, can you hear me now? Okay.
Yes.
Yeah, okay, because I cannot see you anymore. I can only see the screen, but if you see the screen and hear me, then everything's okay. So this is where the plume pushes, and it pushes gonna push the plates apart, and we'll see what happens then. So I'm just explaining this now. Okay, so this is India here, and it's at the southern tip of India, and up here, this is basically Tethys, so this is former ocean floor, and on Africa plate, you have, well, you have more continental material, but we focus here on the Indian plate motion. In the end, it turns out that the relative plate motion is important. Okay, so now I push this, and you see what happens is that you get, on one hand, you get a divergence here, but you get convergence up here. So basically the plate, when it moves and we push it on one side, then you also induce a rotational component. So you can try that yourself. Same for Africa. Also, if you push it this way, then it's moving this way up here. So you get convergence. But the point is that this amount of convergence, or the part of the plate boundary where convergence occurs, is shorter really than where it's observed, right? So the pivot point is really should be somewhere, or the Euler rotation pole should really be something further south. So what I do next is I sort of simulate the in the stronger coupling of the continental lithosphere by putting something underneath and then let it rotate on this thing. So this is like how the Indian lithosphere is thought to couple to the underlying mantle stronger, and the rest being decoupled, which is of course a strong simplification and much more extreme than it is in reality. But in principle, this is the idea I have. And now, of course, that's just this kind of qualitative experiment is still a bit too simple, and so that's why I went on to develop a mathematical or analytical model how to treat this. So. So let's hope whether this works now with the Datei speichern. Okay, and this point appears again, then I have to go out finally. So the rising plume head pushes material ahead into the asthenosphere on which the plates glide. So basically, we take the size of the plume head with a radius of 500 kilometers, which is a kind of realistic assumption, and we say that whole plume head feeds into the asthenosphere, and we assume a parabolic flow profile in the asthenosphere. So once the plume head has fed into the asthenosphere, the total volume flux rate is 2/3 times velocity in the middle of the channel times 2 pi d distance from the plume times the thickness of the asthenosphere, and the 2/3 that comes from the parabolic flow profile. Now this is the volume flux rate. Then the time integral, the total volume flux needs to be equal to the volume of the plume head. So the displacement in the middle of the velocity channel, the integral of the velocity over time relates in this way to the radius of the plume head, the thickness and the distance. So it gets less with distance, as we see. Then we can compute, if it's a parabolic flow profile, we can compute the displacement gradient at the top of the channel. And if you take a viscosity of the channel, we can then compute the time integral of stress acting on the plate at any position. So time integral of stress acting on the plate is again here described in this way. So this is the stress locally, and then we integrate this stress to a torque acting from the plate, acting on the plate from the plume. So this is the plume torque, is just the integral over radius times the displacement. And we say we limit this to 2,400 kilometers within the plume, which is of course a bit arbitrary, but because eventually the plume material will not just keep flowing in the asthenosphere, but go down in the mantle. And from other work, 2,400 kilometers seems like a realistic number. So we can compute the force, the torque of the plume in this way. And can be rewritten like this if you take this equation again. Then now this is the torque that acts on the plume. So now we say this torque is balanced by the time integrated torque acting from the plume. Now we say this torque is balanced by the torque of the plate moving over the shearing asthenosphere. So in contrast to before where we had this Poiseuille type flow, now we have a Couette type flow with a shear flow over a viscous asthenosphere. And they say the shearing occurs over a height hs, which is not necessarily the same as in the other case. So again, we can get a displacement, gradient, and we can get a time integral of the stress by multiplying with the viscosity. And from the time integral of stress, we can again, in a similar way as before, compute the time integral of the torque and the x of the plate motion, which can just be described as omega plate rotation times r position vector. Yes, and the goal is now to find the omega such that the two torques are equal, such that there is plate balance. And it's probably kind of obvious how to do this. We set up an equation or three equations for three unknowns. First, we take a omega 0 with rotation around the x-axis. So x-axis being the axis at the equator and 0 degrees north. So we can compute the tx in this way, display. And we have ex here, and in analogy ty and tz, and then we set t plume equals omega x divided by omega 0 times tx plus this and this. And these are three equations, and the three unknowns are omega x, omega y, omega c. Now, the thing is that omega 0 cancels out, eta 0 cancels out because it appears in both ways in both torques. And we can find the omega with three equations for three unknowns, and the result only depend on geometry. What time is it now? I think it's a quarter to. No, it's 34. Okay, so I still have time. Sorry. Right. So result only depends on geometry, and then what I did is I put the plume here at this plates where it's reconstructed in a slab-fitted mantle frame, and I reconstructed the plates in the same reference frame. And I used the plate geometry I got from Daue at 105 million years. And in this way, I can then compute the total amount of plate motion that's induced by the plume feeding into the asthenosphere. Now, I have to, of course, say that this is a simplification. We only consider the plume push and the plate push. We don't consider that there is any friction along the plate boundary here. So if there is any friction that hinders this convergence, it will not happen. But basically, here, this is the one limiting case that we say it's weak anyway, and we just consider how much maximally you can cause convergence. Later on, at the very end, I will talk a bit about how much stress you can actually induce at this plate boundary, whether this is sufficient. But what we see basically is you can get as, this is just a, well, this is basically just reproducing the first part of my kitchen table counter experiment, but this is now in spherical geometry. And you see that you have the Euler rotation pole of the relative rotation up here, and you can only in this part, you can get this convergence. So going back, how can we get more of this convergence? So again, a velocity gradient in the shear flow and the shear stress are computed in this way. And now we say we have a viscosity structure like this way. We don't have a simple astenospheric shear, and we have the velocity gradient versus depth by a plate moving over this viscosity structure. Now the shear stress should be independent of depth, so that the stress is transferred all through the mantle. And so shear stress is equal to viscosity times velocity gradient. So and if we integrate this again with time, then, or integrate this with depth, then we get that the velocity is equal to the integral of velocity gradient with depth, and velocity gradient is 1 over viscosity. So velocity at the surface is F divided by A times the integral over the viscosity over 1 over viscosity. And we set this by definition equal to HS, a equivalent asthenosphere thickness divided by eta 0, whereby eta 0 is the viscosity just below the lithosphere, so just up here. And in this way, if we solve this for HS, for this viscosity structure, we get that the equivalent asthenosphere thickness is about 200 kilometers. Now, we can redo this with a variable lithosphere thickness. So we just compute, going back, solving this for F over A by bringing bringing this integral over to the other side, but then varying the depth where we start this integration. And then we find that this F over A traction is also different depending on how thick the lithosphere is and how strong the coupling is of the lithosphere with the underlying mantle. So for very thin lithosphere, we get comparatively weak coupling, but for thicker lithosphere, about 240 kilometer, which is the sort of the maximum estimate, we get about 3 times as strong coupling. Right, so thicker lithosphere couples better to the mantle. And how can we get lithosphere thickness? This is from a paper I had in 2016. It's based on seismic tomography, and we essentially equate temperature to seismic velocity. That's the idea. But then this is a temperature anomaly relative to a reference temperature profile. So this is a reference profile, and from the seismic anomaly, you can get and calculate the deviation, and you can get the actual temperature, the given depth. And you say that a certain temperature you assign to the base of the lithosphere. So depending on the seismic velocities, you can compute the thickness of the lithosphere. So drawn in a different way is that this is the reference profile. So if the seismic velocity is above this profile, then you're within the lithosphere. If it's below this profile, then you're outside. So in order to have a thin lithosphere, you need to have a very strongly negative seismic velocity anomaly, and a very strongly positive seismic velocity anomaly. In order to have a thick lithosphere, you need to have a very strongly negative one. So basically, this is how we can compute the lithosphere thickness, and then we just rotate those lithosphere thickness back in time in order to get a distribution 105 million years ago. For the ocean, we use a backward rotated present day age grid, but we also account for the different age where possible. And where there is subduction, the ocean floor has been subducted, and we don't have age constraint, we assume a constant lithosphere thickness. Now we take this different coupling factor at different locations. So the idea, again, shown in this graph here, is a plume pushing towards the side. You have the cratonic root sort of anchoring, and the idea is whether you can then rotate the plate around here, like in this experiment where you have this penny fixed here, and then you get this rotation to get subduction everywhere here, and you get convergence here. So could the India plate be pinned by the India craton? Now, the result with this assumption is that it's a bit disappointing because the coupling differences are not strong enough, and there is only this part, very small part, that has increased coupling, and the result looks almost indistinguishable than before. And then, well, then Tao has said, well, can't we get this modify the model to still get what I want? And I thought of, well, okay, I can make the differences a lot stronger. This is, of course, I don't really believe it, but who knows, maybe through some nonlinear effects, you get some really weak lithosphere in some places where things start moving, maybe some feedback mechanism, and you get really strong coupling in other regions. So I said, what I do now is I increase the coupling by a factor 10 wherever the lithosphere thickness exceeds 100 kilometers. These are the brown areas shown, and is reduced to a factor 1/10 wherever is less. So instead of factor 3 difference, you get a factor 100 difference in coupling. And now it works better. So you can shift the pole, the Euler pole of relative rotation further south. It's still not as far south as we would want, but we get it somewhere closer. And then, of course, one can argue that once a subduction has been initiated, it's an additional force, and there may be extra forces from ridge push. And so at least the plume could help to initiate the subduction. Right. Finally, the last point is that, again, showing these arrows are the total amounts of convergence I can get with a 500 kilometer radius plume head if there is only the balancing between the plume push and the plate friction at the base. And this is, at least up here, it's a few hundred kilometers, so it would be in excess of 100 kilometer convergence, what you would need in order to start self-sustaining subduction. So this is how much you can get. Now the question is how much force you can generate. And in this way, I did another very simple, well, sort of just the back of the envelope calculation, how much force stress the plume can induce. So I assume that half of the plume pushing force and torque acts on the India plate, and take just that the force from the plume head rising can push half of it, can push the India plate this way. And then you take the lever arm 4,000 kilometers, and you get a torque of 3 × 10⁻26 Newton meters. And you assume that this torque is then counterbalanced by a compressive stress acting on the convergent part of the boundary. Again, this is the other extreme. You don't assume that there's any friction beneath you. Basically, it's like, just like in this experiment with the penny, you have sort of pinned the plate on one place, and it can freely rotate. So it's only the plume pushing and then the plate boundary convergence. So there's certainly a maximum estimate of how much stress you can generate at plate boundary. And then doing the simple math, I can get that stress is about 240 megapascal. But if we get this much stress, it would be sufficient to overcome the frictional resistance between the subduction and the overriding plate, which is estimated in the order of tens of megapascal. Of course, this is, as I said, it's a simplification, because in reality, only a fraction of the torque will be balanced at the convergent boundary. And also the plate boundary already needs to be weak prior to subduction initiation. So in this way, I can't model really subduction initiation, because you already need to have a plate boundary that's weak with an estimated friction of tens of megapascals. And then perhaps this additional torque may be sufficient to actually cause this a few hundred kilometer of convergence, which could then help to induce subduction initiation. Right, so just to summarize, the new modeling shows the cratonic keel of India and Africa may form pivots, that the east-west India convergence in the Tethys Ocean can be plausibly explained by plume push, and that plumes may drive the formation of hemispheric plate boundaries. And by inference, the idea is also that plumes may have played a role in the formation of initiation of mosaics of tectonic plates. So going further back in time, because in early Earth history, of course, there were no plate boundary to begin with, but there were plumes. And so this is one mechanism which could have also played a role perhaps in the early Earth. So thank you. This is all I wanted to say for today.